Thank you very much. I'm Dr. Canan Aksoy. I am working for Karadeniz Technical University in Turkey. And today, my talk will be related to superconducting addition effect on microstructural and superconducting properties of thin indium solder joints. My outlines are why we need solder joints, and I'm going to talk about some lattice solder joints and mostly used solders. And I'm going to talk about some findings with candidate lattice solders, and I will talk about the current experiment, and I will conclude with resultant discussion. So the question is, why do we need solder joints? The basic principle of electromagnet is to pass a current from the wire coil. You always need a joint. And if the joint has a resistance, the current will decay in time. But if the joint is superconducting, the current will flow continuously. For this, many years, researchers focus on the discover new techniques as a joint. So today I am going to talk about the solder joints. So soldering is the standard jointing method to produce persistent joints between low temperature superconducting wires and to integrate superconducting wires into the large magnets. And the magnets terminals must be connected in order to confine the supercurrent to the circuit. And superconducting solders must have high critical density and HC2 for being useful for niobium time wires. And the preference resistance for the joint must be lower than 10 to the minus 12 ohm to operate in persistent mode for large magnets, MRI scanners, NMR system, and long power cables. So, for 60s, researchers focused on new solder materials, to find new solder materials. And they discovered lead bismuth and lead tin. And bismuth tin. And after this discovery, bismuth tin and lead bismuth showed quite excellent physical and superconducting properties. However, recent concern on the toxic elements and environmental concerns, researchers try to find new kind of superconducting solders to replace lead including solders. So, or lead-free joints somehow. And what we did before, we did focus on commercial solder first to explore them, whether they are useful for superconducting applications. And we found that they can be useful for aerospace applications, but not superconducting phase. And then we focus on the literature, and we find that lead bismuth is quite efficient. It's a leader, and after thin indium solders showing good superconducting properties. And following, you are seeing tin-based solders. So lead bismuth is quite efficient because it's carrying 1000 amp at 4.2 Kelvin and 1 Tesla. So what we did, we focus on the thin indium system because it has also very good physical properties, because it has higher ductility and low melting point, better wettability, longer fatigue, and relatively high TC. Low melting point is also quite important for the superconducting solders because low temperature superconductors has eutectic composition and one or two phases generally superconducting. And we focus on the thin indium in our previous research, we focus on the tin indium solder system, and we did very extensive research on this. You can see in the papers, and we found that this beta phase, the majority beta phase, showing the best superconducting properties. And then we, in this research, we focus on this composition. And we decided whether we can improve its properties by adding third addition. So what we did, we add niobium, silver, copper, graphene, and magnesium diboride to tin indium. But we add very low content to see what is the interaction between tin indium and the other materials. And also, in our curiosity, we add lead, but very little part. And the experiment is, we just mixed the powders, tin indium, the other elements, actually one elements, and then we put them in the crucible and waited 1 hour at 400 Celsius, because the operation temperature for low temperature wires is 400. And then we casted the solders in a quartz tube as a 2 millimeter for magnetic measurements. So we did macrostructural and superconducting characterization, and the results are shown here. In the first graph is belong to XRD of X-ray diffraction patterns of tin indium, and the other one is the addition materials. And in here, you can see the beta phase and the gamma phase. It's stars and plus. And in here, the niobium, lead, silver, copper, and magnesium diboride and graphene. And the intensity of the gamma phase and beta phase reduce when the samples dissolve in the tin solution. Sorry. So let's have a look at the thermal cycle. And in thermal cycle, the low temperature is quite important, but we know already silver is quite efficient to reduce the melting point. And in here, so we don't see rise in here. And then we found that also let's show the very low temperature. And niobium also a bit increased, and magnesium diboride and graphene show this similar microstructure as a honeycomb, and they show the similar melting point. So with SEM and EDX maps shows that the niobium not very frequently dissolving into tin indium matrix, but in the melting point, it shows that maybe it reduced a little bit, but it's not appear very well. But in here, they are 98% is niobium just stayed in the microstructure. And the silver copper one, this is very nice picture here actually, because silver dissolved very nicely. Maybe if we wait more than 1 hour, we can see the better results than this. But it's still showing the dissolved and dissolved in the tin indium system. And the graphene is actually, we were very curious about this, and we found that it's really difficult to catch the carbon peaks from the EDX maps, but we can see from these maps and these discrete maps, and in here the colored elemental maps. The yellow one belongs to oxygen, and the orange one belongs to carbon one. And we found that its distribution is quite well actually, but maybe we need more time. Maybe higher temperature can be effective for seeing the dissolution of the graphene in thin endolymph system. So next one is belong to lead. So we are trying to away from lead. However, the small addition, very small addition, 2% of addition of lead also show the excellent solubility in thin endolymph system. You are seeing in the discrete maps in here and in the system as well. So another nice results come from the magnesium diboride. Magnesium diboride is also separated very quite well into the thin endolymph system. And in here, you are seeing some not reactive particles. However, the magnesium particle is, just separated the system. So the superconducting results quite interesting here. The resistivity versus temperature results show that the best winner in here actually the lead one. However, it shows resistance below the critical temperature, which is not wanted for the for operation systems. After we can see in here the next one is the purple one, the graphene. Graphene is actually showing a bit promising, but we need, as I said before, we need to try for maybe extended time, or maybe we have to play its temperature. So other one is silver copper, and actually the best is going to actually magnesium diboride. Let's have a look to magnetization and temperature plot here, and it shows that the strength of the strength against the magnetic field is actually the best one is the lead one, and then we are seeing they are quite weak against the magnetic field, and then we can see also here critical current density results here, and actually this small amount of lead also showing the very higher results than the others. And you can see also here the competition between the green and the blue land belongs to lead and magnesium diboride. And we show the results actually. We observed magnesium diboride has the highest strength against the magnetic field here. So also magnesium diboride has the highest BC2, as I said before. And next slide. And as a summary, you are seeing here the results. The lowest melting temperature belongs to silver copper, and the highest critical transition temperatures belongs to lead. And the BC2 is highest one is quite high actually, the magnesium diboride. And we are seeing here also 1.5 Tesla also show nice magnetic field in here. And then the JC showing the best properties in here with lead. Yes. So, as my conclusion, I'm going to say The third addition improves the superconducting properties such as Tc and Bc2, and the third addition with high solubility have lower melting point. And Bc2 and of magnesium diboride addition to tin indium is higher than tin indium, which shows that HTC powders can be promised as an additional material. I can say this because we have already did this experiment, but we haven't got all the results, so I couldn't show them in here. So low addition of lead with good solubility is also improved the superconducting properties of tin indium. And at this end of this experiment, we decide we need to extend the operation temperature to see maybe very good results. Thank you very much. In here, actually, from the results, we are saying in some way it dissolved. But we need to, focus on the phase maps to see the exact results. In this condition, I haven't got this instrument. So, but the results. Yeah. Let me back to it. All right, just a minute. I think this one, yes. Actually, it shows that some unreacted particles in here, and it shows that we need maybe more time to see the exact results for magnesium diboride. But it's changed the superconducting properties, so maybe we can say the limited solubility of magnesium diboride maybe in the tin indium matrix. I can say it like that. Yeah. Yes, maybe there is another, phase appears. Yeah, sure. It's not going well. Just a minute. Yes, here. Yeah, we have to work on this because the results are, just surprised us. So we are just trying to find an optimum way for this actually. Yeah. Yeah. You are seeing in here also some, maybe indium is not showing the lower, but in 14, in tin constant, maybe it shows a bit get lower. So maybe low solubility is, or we can say limited solubility is happen in this solder. Okay. Thank you very much.